Okay, so we're looking at the November 2016 grade 11 paper, and this is a question on diffraction. And it says two learners investigate the effect of slit width on degree of diffraction. And they use green light with a wavelength of 520 nanometers. They set up an experiment as shown below and measure the position of the first dark line from the center of the bright central band when changing the slit width. Okay, so if we just think about this section on diffraction and Huygens principle, what would happen? They told us that we are using green light. And remember, the light source always needs to be a monochromatic light source. So monochromatic meaning light of a single color or frequency. And when the light shines through the slit, what's going to happen is bending or diffraction would take place. But according to Huygens' principle, every point on the wavefront acts as a source of secondary wavelets. So you would get each wave giving rise to new waves. And when that happens, interference or superposition of waves takes place. Interference/superposition. And we remember from grade 10 that when waves interfere or superimpose, then either constructive interference would take place or destructive interference would take place. And the dark bands that we see on the screen are a result of destructive interference. And the bright bands that we see on the screen are a result of constructive interference. So wherever waves meet in phase, constructive interference, it would result in bright bands. And by bright, we mean the color of the light. So in this case, they are showing us that this is the pattern, and we know the pattern always has a broad central bright band. So here's our broad central band, and it's always the color of the light. So we used green light, so it's a bright green color. And then on either side of this, we would have alternating dark and bright bands that are narrower than the central broad band. So we would have a dark band and then a green band again, a dark band and a green band, dark band and a green band, and the pattern would continue. You will notice that the dark and the green bands on either side of the broad band are narrower than the central bright band, and that would be the pattern. So make sure that you are able to describe the pattern for 3 marks, because it's quite easy to do and important that you get those marks. And remember, the dark bands are a result of destructive interference when the waves meet out of phase on the screen, and the bright bands are a result of constructive interference when the waves meet in phase on the screen. Now, there are 2 factors that affect diffraction. And the meaning of diffraction is the bending of light. If there's a lot of diffraction, what does that mean? That means there would be broader bands being formed on the screen. So greater diffraction means broader bands. And there are 2 factors that affect diffraction. The first factor is the wavelength or lambda of the light. And the diffraction is directly proportional to the wavelength. So the greater the wavelength, the greater the diffraction. And when we investigate the relationship between the wavelength of the light and diffraction, then we would keep slit width constant. So by slit width, we mean the width of the slit through which light passes. The second factor that affects diffraction is the slit width. And this time, the diffraction is inversely proportional to slit width. So diffraction is inversely proportional to slit width. That means if I have a very big slit width, then we would have less diffraction. And what does it mean to have less diffraction? That means we would have narrower bands on the screen. Okay. So in this question, they're saying that 2 learners investigate the effect of slit width. So they are investigating slit width as the factor on degree of diffraction, and they use green light with a wavelength of 520 nanometers. The following results are obtained. State Huygens principle in words, and that is a definition. Determine the independent variable. So independent variable would be the variable they are investigating, the variable that they change in each experiment. And to get this, we would always look at the data on the table, and we can see from the table that in experiment 1 they use a slit width of 5,3 exponent minus 5. In experiment 2 they used 4,9 exponent minus 5, and in experiment 3 they used 4,2 exponent minus 5. So each time they changed slit width. So that would make slit width the independent variable. Dependent variable is what they measured each time. And it says they measured the position of the first dark line from the center and in millimeters. So they wanted to see from the center how far away was the first dark line. So that angle, that distance there. So this would enable them to determine how much diffraction occurred, because remember what we said. We said that the more diffraction, the broader the bands, and the less diffraction, the narrower bands. So they were measuring to see how much diffraction took place. So diffraction would be the dependent variable. It is what they measure in each experiment. And the controlled variable, so if we are changing slit width and we are measuring diffraction, then the third factor would be kept constant. We would have to keep wavelength, lambda, constant. Likewise, if we were doing an experiment where we are investigating the relationship between the wavelength and diffraction, then slit width would be kept constant. So remember, there are two factors that affect diffraction. So if we are investigating one factor, then the second factor would have to be kept constant. Given a conclusion for the results obtained, we can see here that slit width is decreasing if we look at the values on the table. So we would start off by saying, as slit width decreases, so in our conclusion we are talking about the slit width, our independent variable. And now we're going to look at the data. What happens? And we can see that the position increases. So that means that the band gets broader. We would have the position of first dark band increases. So you are basically interpreting the information they gave. You are telling them that as the slit width decreases, the position of the first dark band increases. So that actually means that we have broader bands. And broader bands means more diffraction. And this makes sense because if we look here, where we discussed the factor of the effect of slit width on diffraction, we said that diffraction is inversely proportional to slit width. So we can conclude by saying diffraction is inversely proportional to slit width when a wavelength is constant. And we know that the wavelength is constant because in the beginning of the question they said we used a wavelength of 520 nanometers, and in the data on the table they didn't tell us anything about the wavelength changing. They only changed the slit width. 7.4.1, how will the pattern on the screen change if red light is used instead of green light? And they're showing us the wavelength of red light, and we can immediately see that red light has a higher wavelength. Red light has a higher wavelength than green, and the relationship between wavelength and diffraction was directly proportional. So we can say diffraction is directly proportional to wavelength, and this time we would mention that slit width constant. So whenever you use a proportionality relationship, you would mention both factors and also mention the third factor that is constant. So red light has a higher wavelength. Diffraction is directly proportional to wavelength when slit width is constant. So, and the question they had wanted to know, how will the pattern change? So there will be more diffraction, and more diffraction means a broader central bright band. That would be the third mark. So how will the pattern on the screen change? That answer 7.4.1, a broader central band. Explain the answer to 7.4.1. We would say red light has a greater wavelength and diffraction is directly proportional to wavelength. And actually, if we look, they had given 2 marks. How will the pattern change? So there would be one more thing we need to mention here. The broad central bright band, it would be a broader central band, and this time the bright bands would be red. So that would be the second mark. The bright bands would be red. Remember, the first time they used green light, so the bright bands were green when constructive interference took place. And this time when they changed to red light, 2 things would happen. There would now be a broader central band because of more diffraction, we said, and the bright bands would now be red instead of green. Okay, I hope you found this video beneficial. Please like if you did, subscribe so that you don't miss future videos, and share this video with as many of your friends as you can so that more people benefit from these lessons.